In this video, I'm going to look at an algebraic application of Fermat's little theorem. So let's have a look at our question. It says show that 3 to the power of n squared subtract 1 is congruent to 1 mod n, where n is a prime not equal to 3. So how are we going to get started? Well, I see a congruence relation with a power in it, so immediately I start thinking of Fermat's little theorem. And actually, if we look at this power, we've got the subtract 1 in there, which does remind me even further of Fermat's little theorem. And on the other side of my congruence relation, we have a 1, which also reminds me of Fermat's little theorem. And then our mod n is a prime number, which once again reminds me of Fermat's little theorem. And also that mod n is related to my power. Okay, because we've got the n squared in there. Now, it doesn't completely match with Fermat's little theorem because of the n squared, because usually it would just be our mod n subtract 1. However, what I think is that makes the 3 to the power of n squared subtract 1 a good start point for my process of showing that this congruence relation is true. So I'm going to start by writing 3 to the power of n squared subtract 1. And I'm going to consider how can I manipulate this so that I've got a power of n subtract 1 instead, and I can maybe use Fermat's little theorem. Well, what I see in my power is the difference of two squares, which is something you should always be looking out for in proof and show that questions because it comes up a lot. So I'm going to factorize it. And if I factorize it, I get 3 to the power of n plus 1 multiplied by n subtract 1, like that. So now the n subtract 1 appears there, but it's not the power on its own. It's still being multiplied by n plus 1. So I need to consider further how I'm going to manipulate this. Well, I could rewrite this as 3 to the power of n subtract 1 to the power of n plus 1. Because when we have a power raised to a power like we've got here, this power multiplies with this one. So therefore, this is equivalent to what is written above it. So now inside my brackets, I have 3 to the power of n subtract 1. So now I can maybe consider how I'm going to use Fermat's little theorem in mod n. So our value of a is our base of our exponential. So a could be equal to 3. And given that in the question n is mentioned to be prime, I'm going to make that my value for p, which will end up being our mod. Now what I have to consider is which of our versions of Fermat's little theorem am I going to use, and to do that I have to consider the highest common factor of a and p, so the highest common factor of 3 and n. So given that n is prime, that means the only factors of n are either 1 or n itself, so the only possible highest common factors of 3 and n would either be the 1 or the n. Now, if it's going to be n, that means that n is going to be a factor of 3. So let's investigate whether that's possible. Now, given that n is not equal to 3, that is what is stated in the original question, there are essentially two scenarios to consider. When n is smaller than 3, so therefore equal to 2, as that's the only prime number smaller than 3, or when n is greater than 3. So if n is equal to 2, well, 2 is not a factor of 3. So therefore, the highest common factor of 3 and n would have to be 1. Now let's consider the scenario when n is greater than 3. Well, if n is bigger than 3, n cannot be a factor of 3. So therefore, n cannot be the highest common factor of 3 and n. So therefore, the highest common factor will have to be 1. So we can conclude in all circumstances for n where n is prime and not equal to 3, the highest common factor must be 1. So I'd say since n is prime and n is not equal to 3. So as a result, I can use the bottom version of Fermat's little theorem here. I can say that our value for a, which is 3, to the power of p subtract 1, so n subtract 1, is congruent to 1 mod n. And I would just say this is by Fermat's little theorem, given that this is a show that question. So I've got 3 to the power of n subtract 1 here, but if we look back at the original show that statement, I do need 3 to the power of n squared subtract 1. So how am I going to make that happen? Well, I'm going to have to consider this statement over here, that 3 to the power of n subtract 1 raised to the power of n plus 1 is equal to 3 to the power of n squared subtract 1. So what I'm going to have to do is raise both sides of my congruence relation to the power of n plus 1. So I'm going to write that 3 to the power of n subtract 1 raised to the power of n plus 1 is congruent to 1 to the power of n plus 1 mod n. And I know that my left-hand side of my congruence relation is equivalent to 3 to the power of n squared subtract 1. And that's going to be congruent to 1 to the power of n plus 1, where 1 to the power of anything is just 1, and it's going to be mod n. And then I've got the full show that statement as required. So I just write as required.